Haha! Hello everyone, how we doing today? Welcome to the stream. Oh, I need to mute that. Okay, there we go. Welcome back to class. I'm so sorry for the mid-semester break. Welcome, Astro. Happy to have you. Very excited to be back on my statistics shenanigans time. Yeah, it's been a while since the last lecture. And unfortunately, I stopped at an inopportune time. Last time we stopped at the first part of hypothesis testing. We stopped at hypothesis testing part 1. And now we're continuing with hypothesis testing part 2. So hopefully, I hope that's okay and that this ends up relatively comprehensible. That's the goal. I think I probably do have a few slides at the start kind of summarizing what happened last time, but that was before winter break. I got swamped last semester and I couldn't have this extra class on my schedule, so I had to cut back a little bit. But now that this semester's calmer, I can do a few more things. Yes. All right, so we are back. Let's talk about hypothesis testing. In statistics, specifically, if you want to get like really specific about it. Haha. Could I wait? I could. But I'm still working on that waiting screen, so until then, we're just going right into it. That's all we're doing. So before, we probably talked a little bit about how hypothesis tests are a method of trying to draw conclusions about entire populations, entire groups of people from sample data. So we're trying to draw conclusions about everybody in the group that we're interested in based on a small subsection of that group. This is by far the single most common way of making, I'm gonna move myself, of making scientific inferences, of trying to, figure out new information in science. It's not the only method that we might use to test hypothesis, but statistical hypothesis testing is like by far the most common, like in psychology, and I think many other fields as well, though I don't have as much experience with that. And a lot of the time we want to draw conclusions about a population, we're maybe testing how some sort of treatment, like some type of therapy or some type of medication helps a population, or whether some sort of intervention of some type can help a population. Or change something in a population, I guess you could say. And I believe last time we talked about the 6 steps of hypothesis testing. I'm doing it in more technical terms on this slide, but next slide I'm going to put it in more sort of like day-to-day, not as technically jargony terms. And of course, different people will split up these steps differently. So this isn't like the be-all end-all. This is just kind of like a general flow of how this tends to go. The first being, of course, you have to establish what your hypothesis is. You can't test a hypothesis if you don't have one. And like, even if you're only testing one hypothesis, you technically have 2. There's 2 possible outcomes. The null hypothesis, which states that nothing happened or there's no difference, and the alternative hypothesis, which states that something does happen. There is some kind of difference or there is a relationship. So step 1, you establish what your hypothesis is. Step 2, you gotta state what is known about the comparison distribution. The comparison distribution is sort of a theoretical set of scores or means or whatever that represents a world where the null is true, where there is no relationship between your variables, or where your independent variable has 0 impact on your dependent variable. Like, what does the world look like, or what should your numbers look like if nothing's happening here, if your hypothesis is completely wrong and there's nothing going on? Step 3, you've got to set your cutoff. So how big of a difference between your groups is big enough for you to reject the null? How extreme of results do you need to get, or how strong does a relationship need to be between 2 variables for you to conclude that relationship is probably real? Because we've talked about this in previous lectures before, but like, there's this thing called sampling error. We're working with a small subsection of a population to draw conclusions about the whole population. And of course, like, 2 or 3 people, or, of course, in the case of psychology, we use bigger samples than that. But, a handful of people is never going to be a perfect representation of the entire population. There's going to be some differences there. So we need to try and be as sure as we can be that any differences or any relationships that we see in our sample are probably real in the population, and not just the fact that samples can be a little wonky sometimes, So we set our cutoff. How big of a deal or how big does this thing need to be, whether it's a difference or a relationship, for us to conclude it's real and probably not just like random noise? After that, well, once we've set our cutoff, we go ahead, we collect our data, and we calculate our statistics. We do our stats, which is most of the series of lectures we'll be talking about, especially from now on. We'll be talking about the doing the stats step specifically, but we're still on the big picture for now, so. Step 5, you got to make a decision. Okay. You've done your stats. You've done your stats. Was your hypothesis supported or not? Yes or no? Did you find evidence for your alternative hypothesis, or do you have to keep the null? Did you not really find anything? And sometimes, sometimes there's the third option where you found something, but it wasn't what you were expecting at all. And maybe I shouldn't say sometimes. That happens actually a shockingly large amount of time in my personal experience. It's weird. And then finally, okay, you've decided whether to reject or fail to reject your hypothesis. Now you finally got to interpret your results. What did you find? What are you looking at? What are you seeing? What do all these numbers that you've just calculated mean? So, plain English version. There we go. Step 1, you got to tell us what differences you expect or what relationships you expect if you're testing like a correlation. And what would it look like if there is no difference? What would it look like if nothing happened, if there is no relationship? Step 2, once you've established what you're expecting to find, both if you find something and if you don't, who are you comparing your sample to and what are they like? So this might be, what do you think the world is like if your medication doesn't do anything? Like what will happen to depression levels before and after if your medication has no impact on depression? What will the relationship between these two variables look like if they're actually completely unrelated? What would you expect to see if nothing's happening here? Step 3, you've got to establish what counts as different or what counts as a real relationship. And I'm mostly going to be talking about in terms of like differences between means right now, but essentially how different is different. At what point do you think a difference is a real difference as opposed to just noise or sampling error? Then you get to collect all your information and do your math. I guess I could change this to just say, get numbers, do math, because that's pretty much what this step is. Then you decide if the groups are different, yes or no, or if you're testing for a correlation, you test to see if there is a correlation. And then you figure out, okay, how are your groups different? Like, assuming that your groups are different, assuming that you rejected the null, you concluded something's going on here. How? What is that difference? So those are our 6 steps of hypothesis testing, broadly speaking. Again, other people might split this up into different steps. This step 3, where you establish whether something's different or not, this can actually vary a lot. And oftentimes, like, well, it doesn't actually vary that much, sorry. It's usually pretty consistent across people doing a bunch of hypothesis tests. In psychology, I've learned from Phi, the neutrophil. Biology tends to use the same thresholds as us as well. I know a lot of disciplines use that, so sometimes that might even be step 1, because it's just kind of assumed this is going to be our cutoff. But sometimes people set different cutoffs for good reasons or for sketchy reasons, usually for good reasons. Anyway, let's go into a bit more detail. So, stating the hypothesis, you've got your null and your alternative hypothesis. Your null hypothesis is nothing's happening. Null as in nothing, empty, nothing's going on. It's stating that in the general population, oh, you think it's 5 standard deviations for particle physics? Ooh, I haven't heard that before. I have never heard 5 standard deviations like specifically. And that's an interesting thing because like, depending on, so like, in psychology, if we're working with population data, we do 1.96 standard deviations, which gives us about a 5% chance of being wrong. But like if we're working with the sample, the number of standard deviations that we're working with changes depending on a lot of things. So like we don't necessarily do it by standard deviations. We're mostly focusing on doing it on like the chance of a false positive. Like what's the probability that we would have randomly selected a sample with that gave us the results we got if nothing was happening here? So it seems like it's a different approach to hypothesis testing, which is really interesting. I'll have to look more into particle physics to find that out. Thank you. That's really interesting. All right, right. So null hypothesis, nothing's going on. Nothing's happening here at all. your manipulation, your independent variable, has zero impact on the dependent variable in the population. So nothing's happening here. Makes no change. You only have two options with the null hypothesis. You can either reject the null hypothesis, which means you've concluded that there is a real difference here, or you can, I guess I should put it, fail to reject is the more common way of putting it, but you can also call it retain the null hypothesis, which is we don't have enough evidence to say there's a real difference. As best as we can tell, there's no difference. We can't be 100% certain these things are the same, but we don't have enough, we're not confident enough to say there's a real difference here. The alternative, or research hypothesis, I've heard it referred to as both the alternative hypothesis and the research hypothesis. This is stating that something will happen. Something will change. Your independent variable did something. It will have some kind of impact on your dependent variable, and this is true for the population as well. So I'm going to be doing examples in this lecture, and because part of my channel sort of ethos, I haven't been doing this as much lately, but like I'm all about anime. My whole goal with this channel was to connect psychology with anime, so of course I'm going to use anime for my example. Psychopaths. One day I'll do a reaction to Psychopaths. One day, or like I'll do some sort of video about Psychopaths. But Psychopaths is a psychological sort of thriller anime, and it's based around this society that has this thing called a crime coefficient. It's kind of like I haven't actually seen Minority Report, but it's my impression that it's kind of similar in where, is it Minority Report? Either way, they have a system that sort of tries to predict who's going to commit a crime before they commit a crime, and they do. Oh, I thought I heard something, sorry. And they do this through something called a crime coefficient. A crime coefficient in Psychopaths is intended to represent the likelihood that somebody will commit a crime in the future. If you watch the actual anime, it's not actually a very good measure of that, and I would love to do a video on that sometime, but we're just going to take this at face value for now. So for the purposes of this example, let's say I'm testing to see whether crime coefficients are a valid predictor of criminality, or at least are related to criminal behavior. So step one, I might state my hypothesis. My sample, for example, might be people who have committed a crime. So these are people who have been convicted of committing some sort of crime. And then my population, which you can think of as my sort of control group, is people who have not committed a crime. The idea here is if we want to figure out if the crime coefficient it really is related to committing crimes, then theoretically, the people who've committed the crime should have a higher average crime coefficient than people who have not committed a crime. So the null hypothesis, of course, would be there's no difference. The crime coefficient means nothing. So the null hypothesis is that people who have committed a crime don't have a higher crime coefficient than people who haven't. You could also think of it as don't have a lower. You just generally, there's no difference. Zero difference in the criminality. Our alternative hypothesis, also known as our research hypothesis, would be something along the lines of people who have committed a crime do have a higher crime coefficient, or do have a different crime coefficient on average than people who haven't committed a crime. That would suggest that maybe there is some credibility to the idea that crime coefficients are related to criminal behavior if people who've committed criminal behaviors are more likely to, or have higher crime coefficients than people who haven't. That's kind of the idea here. All right, so that's step one. We've established our null hypothesis that crime coefficient is, like, criminals do not have any different crime coefficient from people who have not committed a crime. Yeah, it does depend on one's definition of criminal. There are a bunch of like fuzzy bits here, and the anime really gets into like there's a lot of problems with the crime coefficient in the anime. It's actually, I would consider it a not valid measure of criminality. I'll do a full video on it sometime, I really want to, but if you watch Psychopaths, you gradually sort of figure out that the crime coefficient isn't actually measuring somebody's criminal potential. It seems to actually just be a straight up measure of mental well-being. And so it's conflating mental health with criminality, which is deeply problematic and not at all accurate, you know? And also, social credit. It's basically a social credit score. Yeah, exactly, exactly. It's a deeply problematic measure in the show. And also, like, this is not a great study design either, considering people who have been people who have committed a crime, how can we be sure, right? Like, we could operationalize that as they've been convicted of crime, but what if they were falsely accused? What if it was a faulty conviction and they didn't actually commit the crime? We could do it to people who have confessed to committing a crime, but even then, people confess to committing crimes when they haven't actually, either to protect others or, like, for any various reasons. So, like, this is not a great study, and there are a lot of different ways to operationalize a criminal or, like, criminal behavior or whatever. And we can have a debate on that at some point, but somewhat reminded of models that hunt for a G factor of cognition that it all must hinge on a single factor. Yeah, in my experience as a social psychologist, few, if anything, like, in social psychology, it seems basically nothing rests on any one singular factor. That doesn't seem to be the case. Like, even if that factor is, like, just cognition and thoughts, that doesn't seem to, at least in the area of psychology it's obviously way more complicated than this. I'm keeping it simple just for the sake of, like, introducing the concept, but yeah, like, this study would not pass muster for a lot of reasons. This also isn't a true experiment. I haven't manipulated this. I haven't forced people to commit crimes or something to manipulate whether they've committed a crime or not. Yeah, it's not a perfect example for sure. There's a lot of flaws with it, but we're keeping it simple for the sake of, just this and this and this. But there's a lot of interesting directions you could take this for sure. Okay. So step one, we've stated our null hypothesis that the criminal coefficient doesn't differ depending on whether these people have committed a crime or not. And the alternative hypothesis, there is some difference in crime coefficient depending on whether it's the people who have committed a crime or the general population. So the population, people who have not committed a crime, again, we don't know that for sure. We're just assuming they haven't if they haven't been convicted. All right, so step two. We've got to describe our comparison distribution. What does our control group look like? So this is part of helping us determine if our independent variable made a difference. Unlicensedly perceiving and remembering copyrighted material. Oh yeah, I have pirated the material by downloading it into my brain. Anyway, okay. So how do we determine if our independent variable had an impact, if our sample really is different from the population? Sometimes in a true experiment, this will be some sample that we did some manipulation to. Maybe we gave this sample therapy, or we gave this sample medication, or we had this sample sit through a workshop, or we had this sample read a passage or watch a video or do some sort of activity. We've changed something about the sample. And our goal is to compare the sample's measurements where we change something to the population where we haven't changed anything. That's the kind of idea here. The comparison distribution being the population, which in this case, the population, which is serving as the control group because we didn't do whatever it is to the whole population. Now, in the case of this example, we have our sample. These are people who have committed a crime. Maybe we tricked them into committing a crime so it can be a true experiment. The ethics board would not allow that, by the way, but, maybe we manipulated it, maybe we didn't. Maybe we just recruited a bunch of people who have been convicted of crimes. This sample has some sort of crime coefficient, some sort of average crime coefficient, and some sort of variability around that, some standard deviation. The population, this is kind of our control group. These are people who have not committed a crime, theoretically. That is our population information, and they're sort of serving our control group. So let's say, I haven't actually gone back and looked at Psychopaths to figure out if these numbers make a lot of sense in the context of the story, but let's say the average crime coefficient in the general population is 55 with a standard deviation of 9. That is our comparison distribution. We are trying to see if our sample's mean is different from the population mean of 55. That's the goal here. So now that we've figured that out, how different does our sample need to be from that population mean of 55 for us to reject the null? That's step 3. The goal here is, how far away should our sample mean be from the population mean to reject the null or conclude that our sample is different from the population because of our independent variable. In this case, our independent variable being whether these people were committed or convicted of a crime or not. If the null is true, if the sample mean is roughly equal to the population mean, there should be if the null is true, sorry. If the null is true, if crime coefficient doesn't differ between people who've been convicted of crimes in the general population, then there's a super high probability that the sample that I collect of people who have committed a crime, that their average crime coefficient should be close to the population. Because in that case, if the null is true, there really is no difference between these groups. They both, in the population, if I had all the data in the world, would have an average of 55. If the null is true and crime coefficient doesn't differ between these groups, there's a very, very low chance that I would just so happen to get a sample of people whose crime coefficient is meaningfully different from the population. So the idea here is, if the sample's mean falls close to the population mean, that's probably because the null is true, that there is no difference between these groups. If the sample mean is very far away from the population mean, that would be highly unlikely if the null was true. It almost seems more likely in the case that these groups are meaningfully different, because it would be highly unlikely to get that kind of mean if the sample and the population were identical. Which of course brings up the question, okay, how far off does our sample need to be from the population for us to conclude there's actually a difference? Because we've talked about sampling error. Like, samples will always be different from populations because they don't contain the entire population in them. Just because a sample is different from a population doesn't mean anything special's happening, or it doesn't mean your independent variable's done anything. It just means that it's a sample, and sampling error exists. So what we need to look at is, how big of a deal is this difference? Is it a big difference? Is this a very unusual thing that we've observed in a world where there is no difference? Which leads us to something called the alpha level. The alpha level is something that we in statistics use to determine what qualifies as a really highly unusual sample. Like, a sample that would be super unlikely to get in a world where the null is true. A sample that falls really far away from the population mean. That would be really unlikely to pull a sample with that average out of the population. The most common alpha levels that we tend to see, at least in psychology and other disciplines that use frequentist statistics, are alpha of 0.05, or about 5%. Alpha of 0.01 is actually not super common. I don't see that one too often, which is about 1%. And then alpha of 0.001, which is 0.1%, which I'd say is the second most common to 0.05. The idea here is that these alpha levels represent how far away your sample mean has to be from the population mean, or to put it another way, how unlikely it would be for you to get the sample mean you did based on the population. So the idea here is alpha of 0.05 means there needs to be a less than 5% chance that we would have grabbed this sample if the null was true. There needs to be less than a 5% chance we would have seen this sample mean from our sample if there really was no difference between these two groups. In psychology, the standard alpha level is alpha of 0.05. This is by far the most common. If you're reading a paper and they do not tell you the alpha level, you can pretty much assume that it's alpha of 0.05. Like, that's it. If they use another alpha level like 0.1 or 0.001, they will outright tell you, but if they say nothing, assume it's 0.05, because that's the default. The alpha level determines something called the critical region. The critical region is the part of the distribution where if your sample mean falls there, you reject the null. The typical critical region in psychology is here. So these shaded areas, this 0 here represents the population mean. This is sort of, in case of the example, this would be the average crime coefficient in the population, which, I made up the number 55 for that. So in the population, the average crime coefficient is 55. That is the center of the distribution. If I select a random sample of people, it is most likely that their sample mean will fall close to this 55. It's very unlikely that it will fall out in the tails. If you're using an alpha of 0.05, that means you are beyond 1.96 standard deviations in either direction, assuming that you're working with population data. We'll get more into other stuff later, but it would be highly, highly, highly unlikely for your sample to have a z-score to be further from 0 than 1.9 than positive 1.96 or further from 0 than negative 1.96 if the null was true. It would be, with a alpha of 0.05, there's less than a 5% chance that you would have randomly selected a sample with a sample mean that far away from the population mean if the null was true. Alpha 0.01, that's a less than 1% chance that you would have randomly grabbed a sample with a population mean that far, or with a sample mean that far away from the population mean. Alpha 0.001, there's less than a 0.1% chance that you would have randomly selected a sample with a sample mean that different from the population mean. That's the kind of idea here. Like, if your sample mean falls that far away from the middle, something is probably going on here. We can't be 100% sure, but we can be pretty sure that this isn't a fluke. So we've been talking z-scores so far. We haven't gotten to anything beyond that if you have taken some stats class before, but for now we're on z-scores. The z-score that corresponds to an alpha of 0.05 is plus or minus 1.96. At a z of plus or minus 1.96, there's less than a 5% chance, or, well, beyond that, type 1, type 2 binary. There's technically also type 3 and type 4 errors, but I forget exactly which one's which. They get weird. They're like, you rejected the null for... Oh, yeah. No, I agree. I think false positive and false negative makes a heck of a lot more sense than type 1 and type 2. I don't know why we call them type 1 and type 2 as opposed to false positive, false negative, because it's so much easier to mix up type 1 and type 2 than it is to mix up false positive and false negative, but I don't make the rules. If I made the rules, the language would make a hell of a lot more sense, and we would just say false positive and false negative instead of type 1 and type 2. Oh. Anyway, getting down from my soapbox, where were we? All right, okay. So yeah, if you're working with z-scores, if your sample mean falls more than 1.96 standard deviations away from the population mean, there's less than a 5% chance that you would have selected that sample due to chance. There's less than a 5% chance that you would have gotten that sample just randomly. It's still possible, it's just really unlikely. This means if you have an alpha of 0.05, at that point, we say, okay, there's less than a 5% chance that we would have gotten the results that we did by a fluke. It seems really unlikely to us that this is just a coincidence, that this is just a fluke, that this is just a one-off whatever, that this is a type 1 error, a false positive. So at that point, we reject the null. We're pretty confident that something's actually going on here. When I'm trying to figure this out, like, let's say you're taking a stats class and doing assignments, I really like drawing out the distribution and shading in the tails when I'm trying to figure out whether to reject or reject the null, or fail to reject the null, like something like this. And then I figure out where my sample mean falls. If it falls in the shaded region, you reject the null. If it falls in the center of the distribution outside of the shaded region, you fail to reject the null. So let's say the average crime coefficient is 55. Let's say I find that my participants who have been convicted of a crime, their crime coefficient is 85, and 85 falls here on the distribution. Would I reject or would I fail to reject the null? What do you think? Let's see if I can set up a poll. If I can remember how to set up a poll. Do I remember how to set up a poll? Haha! Okay. Reject or fail to reject? Reject. Fail to reject. There we go. All right, so yes. Just to say that again, now that I have the poll up. If the population mean, so the average person in Psychopath's universe has an average crime coefficient of 55, and my participants, my sample who have committed crimes, have an average crime coefficient of 85, which falls roughly here on the distribution. Do I reject or do I fail to reject the null? Let's see. I want to make sure that people have a chance. Looks like we have 3 viewers, but I don't expect all of you to vote in the poll, so that's okay. 2 votes, 1 vote, 2 votes. All right, that's 2/3 of the class, so I'm going to end the poll. You are correct. At this point, we reject the null. We reject the null. So this is in the tail. This would be highly unlikely that we just randomly happen to grab a sample with an average crime coefficient of 85. It's more likely that whether this person's been convicted of a crime or not is the reason for this difference than just we just so happen to randomly pick a sample with an average crime coefficient that high. We reject the null. We conclude it's more likely that there's a real difference here than that this was a fluke. Because this is incredibly improbable, assuming there's no real difference. Now you might notice I have taken this whole 5% probability and I've split it into 2. On the left we have 2.5% and on the right we have 2.5%. So I'm allowing to be that the people who've been convicted with a crime either have an unusually high crime coefficient or an unusually low crime coefficient. I'm allowing for both. We don't always have to do that. There's something called a one-tailed test. A one-tailed test is where you take your entire alpha, your entire probability, and you put it on one side of the distribution. So let's say I only care if the people who've been convicted with a crime have a higher crime coefficient. I don't care if they have a lower crime coefficient than the general population. I only care if it's higher. Then I might do a one-tailed test. I take that entire 5% and put it on the right side. So the entire 5% is all on one side. I would fail to reject the null if my sample had a very, very low crime coefficient. I can only reject the null if it has a very, very high crime coefficient. I only care if it goes one way or the other. This is, you would only do this if you have a very, very strong hypothesis. Typically speaking, in psychology, we would only ever do a one-tailed test if we were so sure that the results could only turn out one way that we think it's actually impossible for it to go any other way. Like say I'm trying to change the reaction time of some of the best gamers on Earth. Competitive gaming requires a really fast reaction time. So if I'm changing their reaction time, it's very unlikely I can speed it up. I can probably only slow it down. That seems like the only possible change I can cause. In that case, I might do a one-tailed test. If there's any possibility it could go in either direction, even if it feels like a really unusual possibility, I would recommend a two-tailed test just to be sure that you don't miss anything. Because you can't distinguish between the sample mean is identical to the population mean and the sample mean is much lower than the population mean with a one-tailed test. You can't do that. You can only notice if it's in the direction you predicted, which is kind of a drawback. Unless it's literally impossible for it to go the other way. Two-tailed test, which is the type that we do by far the most in psychology. You take your alpha of 0.05 and you split it into 2. So the total critical region, the total probability that you will be able to reject the null is still about 5%. But you split it into 2. You take half of that and put it on the low end and half of that and put it on the high end. So this allows me to be right in either direction. I think that people who've been convicted of a crime have a different crime coefficient than the general population. A two-tailed test allows me to tell if it's unusually high compared to the general population, which I suspect the society and psychopaths would predict, or if they're wrong and crime coefficients are unusually low compared to the general population. I can see if it goes either way, and this is really nice, because let me tell you, there's something about master's projects specifically in psychology, but chances are you will get some kind of result, or at least my experience so far on like master's and dissertation has been like, I'll get some kind of result, but it won't be the result I was predicting. It's good to leave your possibilities open, I would say. But general considerations when you're trying to figure out if you want to do a one-tailed test or a two-tailed test. Two-tailed tests are used when you don't know which way the experiment's going to turn out. You may have a strong expectation that it's going to go one way, but if you can't be 100% sure that it's going to go one specific way, if there's any doubt whatsoever that it might possibly go the opposite direction you predicted, even if that seems very unlikely, I would go with a two-tailed test. A more ambiguous case that would also be a great candidate for a two-tailed test would be self-confidence and study habit effectiveness. If you're looking for a relationship, you might predict that higher self-confidence increases your study habit effectiveness because self-confidence is related to self-efficacy, the belief that you can do something, that you can make changes. So more self-confidence might be related to more study habit effectiveness. Or maybe you're confident because you have effective study habits. That could be a positive relationship. But we can also imagine that this could be a negative relationship about equally likely, right? It could be that if you're too confident, you're not going to study all that much. Magneto and the wooden gun. I'm not actually, I don't think I've heard that. I'm not the right kind of nerd for that analogy. Is it like, I know Magneto has magnetic powers, so like, in that case, that could be a one-tailed test, because Magneto either can attract the gun or he can't. He can't It's an old cartoon skit. I'll have to check it out. Actually, theoretically, Magneto could attract or repel the gun. Yeah, so I guess in that, I don't know, two-tailed AK covering my ass, basically. I like to call the two-tailed test the intellectually humble test. The acknowledgement that I don't know how this is going to turn out kind of deal, if that makes sense. But you can also absolutely think of it as covering your ass if you want to frame it that way. Oh yeah, I can stop your gun, but then he freaks out when his magnet powers effect. Oh my gosh, yeah. But yeah, one-tailed tests, typically, only when you think it could only possibly go one way. Oh no. I'll have to check that out after this. But yeah, you can imagine extreme sleep deprivation, not like sleeping a lot, probably can only slow down reaction time. It seems very difficult to believe that not sleeping for 3 days straight would make you able to react to things faster, right? In that case, it might make a lot of sense to do a one-tailed test because it seems almost inconceivable that it could go in any other direction, right? In this class, and in psychology in general, standard of practice is two-tailed tests. So like, you know how I said alpha 0.05 is kind of the default? Like, they won't tell you if their alpha level's 0.05 because that's kind of assumed. It's the same deal here. They will not tell you in a psychology paper if they're doing a two-tailed test because that's just the default. That's just like the assumption. If they don't say anything, it's a two-tailed test. They will say something if it is a one-tailed test. That's the kind of thought here. Now, when you're setting your alpha level, you are determined, so like alpha 0.05, 0.01, 0.001, you are determining the exact size of a difference that you consider significant. My toxic trait is doing one-tailed test and imagine it's the result of my two-tailed test. Fine, I'm going to hunt you down. I have strong feelings on this matter, and I am going to get you. Okay, anyway. Right. I'm gonna tell Psy you said that. I'm gonna tell Psy you said that, and we're both gonna come after you. Okay. Alright, so, when you set your alpha level, which by psychology standard is 0.05, you're setting the exact size of a difference you consider significant. This is when you're determining how big of a difference would be different for you. You can take that entire 5% and put it on one side, which is that one-tailed test, or you can split it into two and split it between both tails, the two-tailed test. Now, there's a concept I kind of alluded to, but haven't really named. There's this thing in statistics called a conservative test. Conservative means that it's harder to reject the null. What this means is like you're being more cautious about rejecting the null. You're being more careful about whether you reject the null or not. Now, theoretically, both of these tests have an equal probability of rejecting the null, if the null's true. Theoretically. But as it so turns out, one of them is actually more conservative than the other. One of them makes it harder to reject the null than the other, even though theoretically they have the same probability of rejecting the null. Interesting, right? So which one is more conservative? I'm doing a poll. One-tailed or two-tailed? Which one do you think makes it harder to reject the null? I'm excited about this because this is the reason why, like, I get annoyed with certain tests and why I think Psy probably would too. Ah ha ha! I see. I see. Hmm. All right, I'm gonna end that poll now. You are correct. The two-tailed test makes it harder to reject the null, which oftentimes when I'm doing this with my undergrads, they'll guess the one-tailed test because, you know, it's only on one side, right? It only goes in one direction. But the fact is, you're only using a one-tailed test if you're already certain it can only go in that one direction. So that doesn't actually really affect it. The reason the two-tailed test is more conservative, that makes it harder to reject the null, is because your sample mean has to be further from the null to reject the null. In a one-tailed test, you just need to get beyond the boundary of z of 1.645. With a two-tailed test, you need to go beyond the boundary of z of 1.96. Your sample mean has to have a bigger difference from the population mean in a two-tailed test than a one-tailed test. And that's why I prefer two-tailed tests. And psychology as a whole, especially lately, prefers two-tailed tests. We like conservative tests these days. Conservative tests, yeah, it makes it harder to reject the null, but if a test is conservative, you can be more reassured that you're probably right. There's less of a chance that you're wrong with a more conservative test because you raised your standards of what counts as a real difference or a real relationship. This is the higher standard version. That's why we default to two-tailed tests. And that's why I'm coming for you, Phi, over using one-tailed tests and reporting them as two-tailed. I'm coming after you. You cannot escape me. Okay. So now we get to the part that is in the thumbnail and that Phi came in talking about. When you decide whether to reject or fail to reject the null, you have 4 possible outcomes. Oh, hello, Mr. Kitty. I'm sorry, Mr. Kitty is joining me. He has seen me teach this class multiple times, but don't trust him. I've never reported as two-tailed to be good. Yeah, I know you were, I figured you were joking about that. I don't think you would do that. You just fantasize. Oh man, the thing is, with at least how psychologists report statistics, we would be able to catch you doing that. Biology, based on the one biology paper that I've read, the way that biologists report it, they would not be able to catch you if you did a one-tailed test and reported it as two-tailed, but psychology reporting, we would be able to catch you. Yeah, Mr. Kitty is here, and he is very... Oh, he's left. He went away. It's okay. I love you, Mr. Kitty. Still an hour until I get to feed you, though. Okay. All right. So when you're deciding whether to reject or fail to reject the null, there are 4 possible outcomes. The rows here, this is what you do. You reject the null, you conclude there's a difference, or you fail to reject the null, you conclude there's no difference. And the columns are what's happening out in the world. Now, of course, we have no idea if this is actually true in the population. Yeah, she's a kitty. We have no idea what's actually happening in the population, but say we were omniscient, we had all knowledge in the world. Column 1 would be, there really is a real difference. Your therapy does have an impact. Crime coefficients are higher in people who've been convicted of crimes, blah, 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 blah. And the second column, no difference, indicates like the null is actually true. There is no difference between these groups. There's no relationship. When you reject the null, and there is a real difference in the population, that is correct. You have concluded that there is a difference, and in fact, there is a real like if you were omniscient, if you had all the knowledge in the world, you would know there was a real difference. Awesome. You thought there's something there, and there is something there. That's great. It's also possible that you fail to reject the null, and in reality, there is no difference. So you've concluded that there's no difference, and there is no difference. Awesome, yeah, that's also a correct decision. I mean, it kind of sucks because that's not nearly as publishable, but like, at least you're right. The trouble comes in these other 2 boxes. First, it could be that you reject the null, you conclude something's happening there, but in reality, nothing's happening. I conclude that people who've been convicted of crimes have higher crime coefficients, but in reality, they don't. I conclude that my medication reduces symptoms of depression, when in reality, my medication does nothing. That kind of thing. We call this a false positive. It's a type 1 error is the technical term, but I agree with Phi. I think it makes a heck of a lot more sense to call it a false positive. But if you want to sound smart, you can call it a type 1 error, because that's what statisticians like to call it. Essentially, you think something's there, but it's not. It's kind of like, you know that thing when you're like falling asleep? I think it's called a myoclonic jerk, that thing where you're falling asleep and your body suddenly feels like it's falling. That would be a type 1 error. You feel like something's happening, but it's not. Or like getting a positive pregnancy test when you're not pregnant. That would be a type 1 error. Bayesian statistics. I'm scared of Bayesian statistics. This is my scared face. I'm scared of Bayesian stats. One day I'll learn Bayesian stats. Maybe I'll do a series of streams after this where we learn Bayesian stats together, but I deeply fear Bayesian statistics. I'm not gonna lie. I'm sorry. I'm a frequentist. I know. I am ashamed. Anyway. I'm gonna pretend Bayesian is not here. Bayesian is not in the rooms with us. Bayesian stats for Valentine's Day. Oh, if I had time to prepare that, that would be very funny. I think Z has taken some Bayesian classes. I should bug Z. I remember when we first met, Z was like, oh, can you help me with Bayesian stats? And I'm like, no. I'm sorry. Oh. I don't know what internet subculture would be notorious for using Bayesian stats, and I get the sense that I don't want to find out. I get the sense that I'm happier not knowing. Oh no. Anyway, right. False positive, you reject the null, but in reality, nothing's happening. It's a false alarm. The other possibility, the other way you can be wrong, is a type 2 error, which I think it makes a lot more sense when you just call it a false negative. This is when you don't think anything's there, but there is something there. You fail to reject the null, when in reality there is a difference. You didn't see any evidence that your medication reduced depression, but it actually does. You didn't find any difference in crime coefficients between people convicted of a crime and people not, but there is actually a difference there. So like getting a negative pregnancy test, but you're actually pregnant. Or like, this happens a lot, I feel like, in horror movies. You search the room for the killer or the ghost and you don't find it, but actually the killer's in the room with you. Yeah. So yeah. If you reject the null, but there's nothing going on, that's a false positive, type 1 error. If you fail to reject the null, but there is something happening, that's a false negative, a type 2 error. If you reject the null and something's happening, good job, you're right. If you fail to reject the null and nothing's happening, good job, you're right. There we go. So let's talk about some of the perils of type 1 error. I think, I'm not sure if Psy's talked about this study. I love this study so much. So, neuroscience has had a problem. Psych claiming type 1s are adaptive. I have heard that. I have heard that Psych claiming type 1 errors, like thinking that something's in the grass about to attack you when it's not, is adaptive kind of deal, because it helped keep our ancestors on alert or something. Yeah, I have heard that argument as well. Anyway, let me talk about this wild study by Bennett, Beard, Miller, and Wolford. So for a long time, neuroscience has had this problem where a lot of the time they are looking for relationships in activation between different areas of the brain. And areas, they call them voxels. There's like a lot of these distinct little bits of the brain. fMRIs are a way of measuring brain activity while also looking at where in the brain it's happening. And fMRIs use these voxels to determine where this is happening. And a lot of the time, neuroscientists would be looking for any relationships that they could find. And even if they're only looking in a specific area of the brain, there's still a lot of voxels. You can think of voxels as kind of like pixels, I guess. There's still a lot of them, even in that tiny area of the brain. And so what they do is they just like do all these statistical tests, looking for any relationship that they could find. And there's a problem with this. Each individual statistical test has a 5% chance of making a type 1 error, assuming you're using that standard alpha of 0.05. So if you do thousands of statistical tests, that 5% is going to add up, right? You're going to get a lot of type 1 errors. You're going to get a lot of false positives. So these people really wanted to like say, hey, we need to start worrying about this. We need to start being more careful about type 1 error. So what they did was they took one mature Atlantic salmon. This specifically, I believe, they got this salmon from the grocery store. So this was very much a dead fish. They took a literal dead fish and they put it in the fMRI and they analyzed it using the standard methods in neuroscience. And they found evidence of brain activity in this dead fish, which obviously, like, was not happening. But because of type 1 errors, they were still finding this. So that's one problem with type 1 errors. Yeah. Isn't it wild? Isn't that crazy? That's one of the perils of type 1 errors. You run too many statistical tests, you're going to get type 1 errors. And this was a big problem with neuroscience for a while. Ever since this study came out, they're at least more aware that this is an issue, but I'm not as familiar with what they're doing to combat it, but it's possible that a lot of older neuroscience findings might be more or less meaningless if they haven't been replicated a lot, because there was a lot of problematic statistical techniques that were being used in neuroscience for a long time. Like, I don't want to say they're all fake, but like, take them with a bit more of a grain of salt, make sure that findings have been replicated, that kind of thing, especially for older papers, because they were not paying as much attention to type 1 error as they really should have been when they were doing their analyses in the past. I think they've improved, is my impression. Especially after this. Like, what are you going to do after this? Just pretend you saw nothing? They saw evidence of empathy and perspective taking in a literal dead fish. Yeah, caution. So you got to be careful about type 1 error. It is a thing that happens, especially if you're doing a lot of tests. You pretend you do not see it. I see nothing. I am taking off my glasses. I see nothing at all. The joke is the glasses aren't necessary. They're fake glasses to make me look smarter. Anyway, yeah, important to take, even with a control though, like even with a control, this is actually, this test that they were doing was looking at signal change. So did this brain have more or less activity over time? I think I also think glasses look nice. Glasses are a very underrated fashion accessory, I would say. And of course, they are very necessary. They're a medical device for a lot of people, but also I know a lot of people who look a lot better with glasses. Not to saying they look bad, but I think glasses just add a certain something, you know. They look really cool. I think we need to have more appreciation also for like the librarian string that goes on the glasses sides that holds them up. I love that thing. They are, yes, glasses are so cool. I agree. I love glasses so much. I don't actually wear glasses. I'm just doing this to look smart because I'm lazy. But like, they look so nice. They look so nice. Like goggles too. I love goggles because they let me see underwater, okay? I appreciate goggles deeply. I think it is awesome. Goggles are great until they start hurting your face, but they are cool. I don't need glasses unless it's late, but I always wear them to exams because it makes me feel smart. Yeah. I think that's a real effect. Okay, this is kind of irrelevant to the lecture, but now that we're on the topic, I need to tell this story because I think it's hilarious. So when you're applying for PhD, it used to be before the pandemic, our program used to fly out potential PhD candidates for an interview. They would fly to our campus and we would interview them in person. And one of the candidates was wearing glasses and he went through the whole interview in glasses and stuff like that. And then he got in. And then when he came back out to look for, like, he was looking for housing, and I decided to meet him for lunch because he was joining my lab. So we met up for lunch, and he wasn't wearing glasses, and I didn't recognize him. And I was like, oh, where are your glasses? And he's like, what? I'm like, where are your glasses? And he's like, oh, I don't actually wear glasses. I don't need glasses. Those glasses were fake. I thought it would, like, activate the halo effect and make me seem smart. He had even changed his profile pic on all of his social media to be him with glasses so people wouldn't catch him until after he made it into school. Oh, I love that story. It was incredible. I think our grad school, our PhD advisor didn't find out about it until like 3 or 4 years in to him being in the program, and when she did, she laughed so hard she cried. It did work. He got in. I'm not saying it was the glasses, but it probably wasn't the glasses, let's be real. Like if you get invited to an interview, especially if they're flying you out, you're basically already in as long as you don't act like a total jerk. At least in my program, but still. Yeah, exactly. Dress for the job you want. Except he never wore the glasses again. He dressed for the job he wanted up until he got the job, at which point he stopped. Which, you know what? Valid. Anyway, okay. I had another story about type 1 error. This was kind of a problem. So this is a much more serious story. This was kind of the goofy type 1 error story. This is more serious. So there's this cardiologist, Dr. Poldermans, and he had this long series of study. There's a Vox article linked in the slides. I have the PDF of the slides uploaded in a Google Drive folder that is linked in the description of the stream. But he did a series of studies showing that beta blockers improved outcomes for heart surgery. And because of this, all these studies, it became European and some US medical committees started recommending taking beta blockers before heart surgery. It turns out this was a type 1 error. Beta blockers did not actually improve outcomes for heart surgery. And in fact, if you did it as a two-tailed test instead of a one-tailed test, beta blockers actually increased the outcome of death and fatality during heart surgery. It actually did the opposite. So it's possible that, like, we don't know for sure what the impact of this was, but it's possible that like thousands of people might have died because of these false positives. Like, we have to be very careful about false positives, is what I'm saying. They can have very severe, dangerous consequences, especially if like you're in medicine or something like that. So be careful. So that was all step 3. Setting your cutoff. Setting your cutoff for what counts as a significant difference. Oh, that was a long, long time. All right, let's go on to step 4. This is we collect our data and we do our stats. I recall 30% false negative rate for rapid antigen COVID tests. Yeah, that's why with COVID tests, they'd always recommend that you take multiple tests. It's the same for pregnancy tests. Like, you gotta keep doing it. Increasing the chance of 20 by 20, or increasing mortality rate by 20 point. I think it was increasing the probability of death by 27%. So increasing the chance as opposed to increasing the mortality rate. So that 27% sounds dramatic, but like you'd have to know the baseline of how common is death already in the first place. If death is only like a 0.0001% chance in this type of surgery, then a 27% increase might not mean a lot. If there's like a 1% chance or like a 10% chance, that 27% start looking a heck of a lot more scary. But it's not like mortality rate plus 27%. It's probability plus 27% from baseline. So could be worse, I guess. Ah, still though, not an ideal outcome. Okay, so you run your data, you collect your data, you get your statistics, you get your sample statistics. So you get your average crime coefficient and the standard deviation of crime coefficients. Just to remind you of the example we were using, we were looking at psychopaths. Do people convicted of a crime have higher crime coefficients than the general population? Because that's kind of the premise that the government was operating under on psychopaths. So then we do your stats. For now, because the only thing that I've gone over in this series is z-scores, if you just have one person, let's say you're only comparing a single person to the general population, you calculate a z-score. You plot your z-score on your comparison distribution, and you see where it falls. Is it in the critical region? Is it that far from the mean? If so, reject the null. If it's closer to the mean than the critical region, if it's inside the body of the distribution, you fail to reject the null. So let's say I found one person, let's say the protagonist of Psychopaths, whose name is escaping me. Is it Akane? I should know this. You'd think I admit, I haven't watched Psychopaths since it came out. It's been a while. You think I would have prepared? Akane, yeah, I was so right. Akane. So let's say we compare Akane to the general population, and we find that Akane's general crime coefficient is 35. And we figure out the z-score for 35 is somewhere like around z of like -3 or something like that. At this point, Akane's score, her z-score, falls in the tails of the distribution. It's in the critical region. At that point, we reject the null, and we can say Akane actually has a lower crime coefficient than the average population, significantly so. So once we figured out the z-score, either for our single individual, or we can do a z-test and find out the z-score for a sample of individuals, we decide whether to reject the null or fail to reject the null. If we reject the null, that's because our sample data, whether it was a single person or a single mean, fell in the critical region. It's beyond our cutoff. And we conclude, okay, our independent variable did predict some kind of difference. In this case, it's not having an effect because like we didn't randomly assign these conditions, but there was a difference between our groups or the individual and the population. There's only a 5% chance that we would have randomly picked somebody or some sample with an average crime coefficient that low or that high. It's highly unlikely that we would have gotten this just due to random chance. So we're concluding that something actually happened here. That's what you mean when you say you reject the null. It's unlikely that we would have gotten these results just due to a coincidence. It's more likely, we think, that our independent variable did something. If you fail to reject the null, let's say your sample mean or that individual falls in the body of the distribution, they're not out in the tails, they're in the middle of the distribution, they're close to the population mean, we fail to reject the null, we don't have enough evidence to say that there's a real difference here. So you've drawn your conclusion, something happened here or something didn't. Next, step 6, say what you found in plain English, or it doesn't have to be English, whatever language you're writing it in, whatever language you're communicating in, say it in that language. Your interpretation shouldn't be full of like jargon and like fancy statistics words. You should try and make it easy to understand, easy enough for somebody who's never taken a stats class to understand what you found, because most of the people who will be using the information that you find in their day-to-day lives probably have not taken a stats class or haven't taken one in a long time and forgotten everything that they learned, So let's do another example. Let's say we have our sample of people who have committed a crime or have been convicted of a crime, and their average crime coefficient is 63. Then we have our population. Their average crime coefficient is 55 with a standard deviation of 9. And let's say we get a result that looks a bit like this. Here's the population mean of 55. Let's say our samples mean fell about here, 63. Let's say it was a z-score of 1.5. That is in the body of the distribution. That, at that point, it's not beyond our cutoff. It doesn't quite make it to the critical region. We would fail to reject the null here. We cannot conclude that anything's special here. We cannot conclude, we don't have enough evidence to say that people who are convicted of a crime have any difference in crime coefficient from the general population. How we doing? I hope everything's making sense. I would normally check in with my class right here, but it feels kind of weird to check in when I know like people can come and go from the stream whenever they feel like it, but everything making sense? And of course, you're welcome to chime in with questions whenever you have any. I'm more than happy to answer questions. Yep. Awesome. Well, good. I'm glad. But yeah, if anything comes up, just shoot me a question in chat and I'll get to it ASAP. All right. So last class, which was, I know, about 1 billion years ago now. That was like last fall. Yeah, I'm following along despite not seeing the last 7. My A-level maths isn't failing me yet. Yay. Great success. All right, so last class, we had done an example where we talked about giving a single person $10 million to see if that person was happier 6 months down the line. So essentially, we were doing a hypothesis test with only one person. And this is what we had. We had a sample mean of 80 on this happiness scale. The person that we gave the $10 million to had an 80 out of whatever on the happiness scale. The population mean on this happiness scale was 70. The standard deviation on the happiness scale was 10. And our sample size was 1 before. What's the deal with the +1 in the denominator for the population mean? The +1 in the denominator for the population mean. Where was this? Where was it? Do you mean like the... All I can think of right now is like the degrees of freedom, like the... Maybe that's too out of scope for this, like... Not here this moment. Okay. Yeah, like, when I think of something 1 in the denominator for something, I'm thinking of like... The standard deviation for a sample is the sum of squares over n minus 1. And this is the bit that's a little weird because like the population one doesn't have the -1, but the sample one does. Is that what you're talking about? That little weird thing here? Might be it. Yeah. I'm not sure. I'll have to look into, because I can't think of anything with the population mean with a +1 on the bottom. But this one, when you're calculating the variance or the standard deviation for a sample, there's like complex mathematical reasons that I don't fully understand for this. But the simpler way of thinking about it is, let's say you're trying to calculate the variability of height, and you've only got a sample. Let's say I've got 20 people in my sample, or something like that. We know that the true range of heights for adult humans is something like, I think it's like 3 foot 8 inches for the shortest person, and like 8 foot 7 inches or something like that for the tallest person. Like, the true range of height in adult humans is incredibly big. But if I randomly select like 20 random people, chances are I'm not getting the extremely, extremely short people or the extremely, extremely tall people. So my estimate of variability is actually going to give me a smaller number than the actual population variability, because I'm not getting the extreme scores, because those are really, really rare. I'm only getting scores that are fairly average for the most part in my sample. And we know that this is like a known problem. We know that samples, their standard deviation and their variance will consistently underestimate the standard deviation and variance in the population, because we're not getting the extremely high and extremely low scores most of the time in our sample. So sort of like the simplified explanation for this n-1, this adding this -1 here, is it's making the denominator of our calculation for variance smaller, which makes the output bigger. It makes the denominator of the fraction smaller, makes the output bigger. It's adjusting for the fact that we know that we're gonna underestimate. So we make the output a little bit bigger so that we're not underestimating the population variability. Apparently there's also some matrix algebra and stuff involved for exactly why they chose to do it this way, but that goes a little over my head, I'm not gonna lie. I hope that helped. I hope that's what you were... But if you think of something, like, if you remember what you're thinking of later and it wasn't this, like, feel free to let me know. Oh, and as n gets bigger, the -1 matters less and less. Exactly, because you've got more and more of the population in it, right? So, like, the bigger the sample you have, the less of a problem this is, because the bigger the sample, the more likely you're going to get those extremely high and extremely low scores. Yes, 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 exactly. Good observation there, Xenotime. Yeah, it's weird. The whole degrees of freedom thing is a little fuzzy, I would say. But yeah, sorry. I think I did the whole thing on that. Have I done that? Or is that an upcoming lecture? I can't remember if I have proper slides on that in a lecture before this or one that's coming in the future. I think that actually might be in Wednesday's lecture or next Monday's, I'm not sure. Sorry. Basically, we know the number's going to be too small, so we adjust the formula to make it a little bigger to adjust for that. It's a biased statistic. It underestimates the true population variance, so we correct for that bias by doing n minus 1 instead of just n. Okay. All right. Oh man, I'm not even... I think I am halfway through. Oh, this is rough. Normally I get through this in one lecture period, and I'm already more than one lecture period through. Oh, no, you're fine. I really, really enjoy tangents. I enjoy tangents, and I'm 29 out of 53. Oh, you've got the slides, huh? Yeah, we're at 29 out of 53, and I can't do math, but I think we're over halfway through. Oh, I'm hoping that some of the later ones are just like, oh yeah, I've got the last 5 slides are just memes where I explain the joke. Okay. So before we did this with a sample of only one person, and we found that this one person who got $10 million was not any happier than the general population 6 months down the line. I enjoy tangents. I can't do math. I mean, that's true. Both of these things are true. I enjoy tangents, and I also can't do math. These things are... I don't know if they're correlated or not, but maybe they are. 6 and 7 are missing from the Google Drive. Yeah, I noticed that just as I was posting this. I'll have to get them up there. Tan X. Oh, yeah. Yeah, I'll get 6 and 7 up there soon. Thank you. I don't even remember too much about that kind of tangent. Anyway, okay, so this time, rather than just having one person, we are bumping the sample up to 25 people. So before, we didn't find that $10 million made this one person happier 6 months down the line, but what if we increase our sample size? To do this, first we have to establish our null and alternative hypothesis. Our null hypothesis here is probably that the $10 million does nothing. The happiness of the 25 people who got the $10 million is no greater or lesser than the general population. It had no impact on their happiness after 6 months. The alternative hypothesis is that it did have some kind of impact. There is some difference in happiness between the sample who got the $10 million and the general population that didn't 6 months down the line. I'm going to leave this as a two-tailed test. It is possible that getting $10 million made people happy even 6 months down the line. But it's also possible that getting $10 million made them less happy 6 months down the line. There's a reason lottery winners hide their identities. It's because a lot of people start coming for them, asking for money. Then you got to worry about the taxes, all this kind of thing. So I'm leaving it open that this money could either improve their lives and make them happier or make them less happy. I'm doing a two-tailed hypothesis here. So that's our hypothesis. Null, this doesn't affect happiness. Alternative, it does. Step 2, we need to describe our comparison distribution. What do people who did not get the $10 million, what does their happiness look like? And I've actually given that to you here. Their average happiness is 70 with a standard deviation of 10. So there's step 2, there's our population data. Step 3, we have to set our cutoff. I'm gonna feel really silly if I have slides for all of this. I don't, good, okay, I don't have to feel silly. Okay, so step 3 of hypothesis testing, we have to set our cutoff. And we're going to use the standard alpha in psychology of 0.05, which corresponds to a Z critical. We call it a critical value because it sets off a critical area of plus or minus 1.96. The Z-score of our sample has to be further from 0 than 1.96 in either direction for us to conclude there's a significant difference. So that's step 3. Step 4, we actually have to do the math. So here we have the formula for a Z-score with a sample. It is the sample mean minus the population mean divided by the standard error, which is our numeric estimate of sampling error. I'm going to move myself down. There we go. Now we do have the sample mean. That's 80. Our 25 people had an average happiness of 80 6 months down the line. We have the population mean, that's 70, but we don't have the standard error yet. So there's the formula for standard error right down there. So we're going to do standard error first. The formula for standard error is the standard deviation of the population divided by the square root of the sample size. The standard deviation of the population is something I gave you. Oh, peeking up. This is me. Hello. I don't want to block anything. I do admit this is kind of cute, though. I'm not going to lie. Okay. Not to toot my own horn or anything. All right. So the standard deviation of the population's 10. On average, happiness scores varied by about 10 points. Divided by the square root of our sample size. This time we have 25 people in our sample. So our sample size, n, is 25. So that becomes 10 divided by the square root of 25. What's the square root of 25? Does anyone know the square root of 25? You know you want to tell me. I promise I know. I'm not asking because I don't know. This is something that I do actually have. I memorize my time too. Thank you! Yeah, it's fine. Sorry, I like doing that to it. No, that doesn't sound right. Xenotime, that sounds incorrect. I mean, we could check with a calculator to be sure, but I'm pretty sure Astrolotropos has it right. I'm pretty sure it's 5. That's what I remember anyway. All right, then we do 10 divided by 5. Our standard error is 2. So on average, we can expect a sample mean to be about 2 points above or below the population mean due to sampling error alone. No one has ever performed a square root. They don't call it a cool root. You know what? Yeah. Okay, so this is like a weird thing, but I did it. I did it right. I'm so excited. You know, my favorite thing to do is to like go into my fellow V-Theorem members' chats on like an alt account and see if they can pronounce my alt account username correctly. And so far, none of them have. And all of them have mispronounced it differently. So I do my utmost to pronounce everyone's names right. 69 is the parallelogram root of 20. Is that true? See, like, I don't know. I don't know anything. I don't know. I'm not a math person. You know, Phi the other day in chat called me and Z the math people of V-Theorem. And I was like, maybe Z is. I'm not. Or I don't know if it was in chat. It was related to something debut. It was related to something to our debut, which is happening on Saturday. We're doing our V-Theorem debut on Saturday. Stats is not math. Stats is not math. I deny it with all of my soul. Stats involves math, but it is not math. It's been fun going in chats and seeing the brief pauses streamers read the names and make a call to try it or not, right? Man, with my students, I have a lot of students with, like, unusual names, and, like, if I know that I'm gonna have to say their name, I will go, and, like, I'll go in my office, and I'll throw on my headphones, and I will listen to a video pronouncing their name, like, on loop for 5 minutes just to make it sure. Right now, none of the other V-Theorem members are streaming any math. Is anyone else even streaming right now? You never know with Psy these days. Psy could be streaming right now, and I would have no idea, but I'm pretty sure it's stupid o'clock in the morning for her. This is literally taught to me in A-level maths with no distinction in the UK. Oh, nice. I never made it to calculus in math. This isn't a secret. I never made it to calculus. It was... I had to take, like, refresher on basic math when I got into undergrad because my math scores were pretty low. Okay, anyway. So, we know our standard error. AP Stats, that class was a complete disaster. I'm so sorry. Calculus is just the math of change. It's easy for you to say when you know what's going on. I have no idea what's going on at any time at all. It's not that Stats is bad. The AP version is just stupid, fair enough. But the name is spooky and psychs people out. I had no idea Americans teach maths. We just had maths. We have, like, levels of math. So there'll be, like... I don't know, there's like... I think you're only required to get through... I don't remember, it depends on the school district. But, like, I only got as far as trigonometry. That's as far as I got. But you could go up to calculus and stuff before going to college. I did get to watch anime in that class when I broke the school Wi-Fi blocker. That's my best memory of AP Psych. I'm having flashbacks to be... Oh, AP Stats. Okay, good. because I was having flashbacks to like when I was a TA in Psych 100, and I would sit in the back of the lecture hall, and I saw somebody watching Madoka Magica in the middle of a lecture, and I'm like, it's a good show, but can you do this at literally any other time? You're not going to be able to see slide through your tears. Definitely not the wildest thing I've seen from the back of a lecture hall, but it stands out to me. Anyway, okay. We had foundation and whatever the one I did was called. It was split maths and further maths for A level, but you needed to do math for future maths. See, all of this just sounds so like as somebody completely unfamiliar with the UK school system, I'm just like, maths is like, we would always call it math class, but we'd know like I'm in trig or I'm in pre-calc or I'm in calc or I'm in whatever. That was an inner city high school. It was pretty above board. Oh, fair enough. Okay. So, z-score is the sample mean minus the population mean over the standard error. Our sample mean here is 80. On average, the people in our sample got a happiness score of 80. Oh gosh, I need to write smaller. Let's write smaller. On average, they got a score of 80. The standard or the population mean was 70, so 80 minus 70 over the standard error that we calculated on the previous slide, which was 2. 80 minus 70 is 10 divided by 2. Our z-score is 5. Assuming I didn't do any math horribly wrong, which I'm never confident about, but you know what? I have this animated, so let's see. I'm gonna erase the ink. I got it right. I did the math right. Okay, so we have our z-score. Our z-score is 5. This means that the people who receive the $10 million, their happiness score is 5 standard deviations above the population mean for happiness, which, if you've taken AP stats, you can probably already figure out, like, this is a pretty big difference, I would say. That's definitely in the tail of the distribution. So now we get to decide whether to reject or fail to reject the null. If our sample z-score is in the tail of the distribution beyond our cutoff, we reject the null. If it's not in the tail, we fail to reject the null. So I'm going to draw our distribution. You don't have to do this, but I think it's pretty helpful. Wait, so it's 5 sigma? Yeah, it's 5 sigma. That's what z-scores are, a measure of distance in units of standard deviation. So a z of positive 5 means your 5 standard deviations are 5 sigma above the mean. Yeah, it's a pretty big z-score. Okay, so here's our distribution. Here's our population mean of 70. Our cutoff for significance is beyond plus or minus 1.96. So we need to be beyond that cutoff. We need to be in the critical region, the shaded area, to reject the null. Good enough for particle physics. Oh, you're right. You said that earlier. No, Astrologopos mentioned that earlier in the stream. It's all coming together. See, this is replicability. This is consensus. Now I am increasingly certain that 5 sigma, that 5 standard deviations above the mean, is significance for particle physics. I learned this. Thank you all for teaching me these things. I feel so smart. I'm gonna tell Z. After the stream, I'm gonna go to Z and be like, I know the standards for significance in particle physics. Are you proud of me? Okay. So the z-score that we calculated was 5. So we are way out here. We are absolutely in the tail of this distribution. That is, we need to make sure how sure we need to make a distribution of how sure we are what the significance thresholds are. That could be fun as well. It would be really fun, actually, to create a distribution that showed all the significance thresholds for different fields. I think that would be really neat. Anyway, long story short, we reject the null. We are definitely in the tail. It would be highly unusual to get a sample mean this high above the population mean just by random chance. 1 out of 3,500,000. Oh my gosh. Look at us go. Look at us go. We're so good at this. I've actually gotten a Cohen's D of... No, actually, no. I was thinking of the wrong thing. But I've seen z-scores bigger than 5. I think the biggest z-score I've seen just like in data that I was personally analyzing was 9, which was pretty impressive. Anyway, So now we interpret our results. Cohen's D's. I'm gonna fight you. Yeah, 9 was wild. It was pretty. It was a very skewed distribution, as you can probably imagine. But the particle physicist, yay! I made the particle physicist proud as a psychologist. This is a delight. Okay, so at this point we can conclude that, but it's true. It's true. I'm sure I've sworn on stream before. Like I have no right to pretend that this is say-so, and I don't really care about monetization, so like follow your dreams, Fi. Make Cohen's D's nuts jokes if you want to. I'm sure Cohen would be proud. I have no idea, actually. Anyway, we have rejected the null. The two populations are significantly different. We've concluded that it's highly unlikely that the difference between our population and the sample was due to chance. We can say with a 5%, or in this case, less than 5% chance of a type 1 error of a false positive, that the 25 people who received the $10 million were happier than the people who did not. This is really important. A lot of people, when I'm like teaching a stats class, or like sometimes when people are writing a paper, they will forget the important step of like putting your results in language that people who aren't familiar with stats can understand. Make sure to do this, or else why did you do all that math? Tell people about it in ways that they can interpret. So like if I said, oh, I found a Z of 5, I rejected the null. I concluded there was a difference between the treatment group and the control group. That doesn't tell you anything. If I say the people who got $10 million, we're pretty sure that the people who got $10 million are happier. No. Oh my gosh, astrologist is just out here calculating all this stuff. You're so powerful. Yeah, it would be highly unlikely that this would have happened by chance. And yeah, it doesn't need to be plain English. These are slides that I've adapted from my stats class that I teach in English, but you are so right. Anglocentric. It's just, you weren't here earlier when I clarified that this is whatever language you're communicating in plain language that your friend who hasn't taken a stats class can understand. Whatever language you're communicating in. Now, I will defend myself, even though I feel like I don't actually need to, but just for the sake of fun, I will defend myself in that the main language of psychology and psychology publications, the sort of international language of psychology, is English. Whether that's how it should be is another matter entirely, but that's how it is. So you must write all papers in Esperanto. Oh no. I don't even know a single word in Esperanto. I know what Esperanto is, but I don't know a single word in Esperanto. But yeah, it kind of, like, I mean, personally, I feel really happy that the international language of psychology is English, because that meant I didn't need to learn a second language, but like, it really isn't fair, you know? It's not fair. The Germans would have gloriously long, complex words for everything. German is such a fun language. It makes me happy. The only languages I can speak any amount of are English and Japanese, though, unfortunately. And I can't speak Japanese well enough to teach statistics in it. Okay, anyway. Right, moving on. Lojban is real. I've never actually heard of that one. The sentence in the blue box could be one word in German. Oh, no. Oh, yeah, probably not, but it's funny to think about. It is designed to be logically consistent, if you don't know. Oh, interesting. I'll have to look into that. I have a friend who's like super into learning languages. I'll ask her about it later. Anyway, okay. So the hiragana and katakana, but my kanji is also really weak. My listening is really good too, but my speaking is not great. But I have hiragana and katakana pretty much down. Anyway, okay. So last time, way long ago, we failed to reject the null. We had the same values for pretty much everything. The only thing that changed was our sample size, but increasing our sample size from 1 to 25 meant that we were able to reject the null when we weren't able to before. Increasing our sample size made it easier for us to find what we found, to detect an effect. This is related to a concept called statistical power that we'll talk about a bit more later. For now, let's do another example. Let's say I want to know if getting a recommendation for a friend increases the likelihood that you'll watch a show. For me, not really. Well, more like I'm weird. Like if somebody recommends a show to me, chances are I will like not start watching it until like 6 months to 3 years later. And when I do, I'll come back to them like, this is great. Why didn't I watch this sooner? And they'll be like, bro. Oh my gosh, that's a long name for a train station. All right, so let's say, I don't know. I have no idea if that's correct. So let's say I want to test if getting a recommendation makes you more likely to watch a show. And I collect a sample of 64 people. And I tell these people that their friend recommended that they watch like some obscure anime like Violinist of Hamlet or something, which I don't know if that's actually obscure, but you know. And let's say the sample said that they gave a likelihood rating of would they watch the show of 7.5. So the sample mean of likelihood of to watch the show is 7.5. It was recommended to me a year ago. You'll get to it eventually. Yeah, that's fair. I keep trying to rewatch it because I want to make a video about it. And like I get like 1 or 2 episodes in and then I just stop. Not that there's anything wrong with it, but yeah. Yeah, Psychopass is like, if you ask people about psychology or psychological anime, Psychopass is one of the main ones they recommend. And I think It Invaded is way better for people who are into psychology and anime. I really love It Invaded. It's so good. I want to rewatch It Invaded. Screw rewatching Psychopass for the second time. Or screw watching Psychopass for the second time. I'm going to rewatch It Invaded for the 5th time. I think that sounds like a great idea. Anyway. So, our samples has a 7.5 likelihood rating of watching the recommended show. Let's say the population has says like, my likelihood of watching, say, Violinist of Hamlet or whatever is 6 out of 10. And the standard deviation is 4, and their likelihood ratings are normally distributed. So unimodal, symmetrical, that fancy distribution that is very fun to draw. 10 out of 10 do recommend this thing. Step 1 of hypothesis testing, we got to state our null and alternative hypothesis. So our first population is people who are told a friend recommended the show. This is our experimental group. And our population, our control group, is people who weren't told about the show or like weren't recommended the show by a friend. The null hypothesis is that there's no difference, that it doesn't matter if a friend recommended it or not, people will be equally likely to say they're going to watch the show. So the mean of population 1, people who were recommended it, and the mean of population 2, people who weren't recommended it, should be about equal. The alternative hypothesis is that being given a recommendation does impact likelihood ratings. I'm going to leave it two-tailed again. It is possible that a friend recommending a show to you will make you more likely to watch it. Or, like, sometimes I get like this. If you recommend me the same show too often, I go full reactance and I will just refuse to watch it. Even if I would have otherwise, you know? So I'm letting it go either way. But either way, I'm still predicting that there is some difference in the likelihood of watching it if you have it recommended to you versus not, whether that makes you more likely to watch it or less likely to watch it. So that's step 1. We've established our hypotheses. Step 2, we describe our comparison distribution. And in this case, I've told you the average likelihood that people watch the show that they report in the population is 6. So the population mean for likelihood of watching The Violinist of Hamlet or whatever is 6. And I've calculated, and then we can calculate the standard error. So we know the standard deviation is 4 for likelihood ratings, and the sample size is 64. The formula for our standard error is the standard deviation over the square root of the sample size. So we can start plugging numbers in. The standard deviation is 4 over the square root of our sample size, which is, we had 64 people. So that's 4 divided by the square root of 64, which is that 8? So square root of 64, 8? I think it's 8. Astraltopos, you know math better than I do. No, I'm not I don't like cold calling. I'm not going to call on anyone in particular. But if somebody could confirm that I have gotten this right. Okay, good. Thank you, Marlon. Thank you, Astrologist. Thank you. I always worry. I was pretty sure I was right, but you never know. One of the Minecraft numbers. This is true. It is one of the Minecraft numbers. All right. And Oh, yes, that's right. Thank you, Xenotime, as well. All right, so 4 divided by 8 is 0.5. So there is our standard error. Our standard error is 0.5. Population mean likelihood is 6 with a standard error of 0.5. And then this is normally distributed. Power of 2 comes second nature to anyone who's meddled with computers long enough. This is true. Probably true. Who needs a calculator when you have nerds in chat? Exactly, you're my calculator now. Thank you so much. Thank you for being my calculator. Or at least checking my math. It is much, much appreciated, because I have zero confidence when it comes to math. All right, yeah, and there it is. There, look, it's confirming on the slides that we got the right answer. Great success. Okay, so that was step 2. We've established what the control group looks like, what the population who hasn't been recommended the show looks like. Now we got to set our cutoff. Well, we're using the typical standard cutoff in psychology of alpha of 0.05, which means our z critical value is plus or minus 1.96. Project idea, a calculator that doesn't show you the answer, it just tells you if you're right or not. I bet I could create that in R. I could create a function for that in R really easily. I could do that. Maybe I should do that. I could even make a Shiny app. I could put it up on a website so anyone can use it. It would be really fun, I'm not gonna lie, and it would be super, super duper easy. It would be like really easy, I think. I might be missing something, but right now the code seems really easy in my head. Anyway, that could be an idea for a stream, and then I could just use that from now on to check my math without... Yeah, okay. So I'm doing two-tailed. I'm allowing it to be that it's an either tail. So I'm splitting that 5%, putting in both tails. Yeah, there's my cutoff. This is the standard cutoff in psychology, at least when we have population data, when we're using a z-test. Things will change when we're working solely with sample data, but we don't need to worry about that until Wednesday. So now we get to do our statistics. Now we need to calculate our z-value. So first, we plug in our sample mean. Our sample mean enjoyment was 7.5, minus the population mean enjoyment, which was 6, over the standard error that we just calculated, which was 0.5. 7.5 minus 6 is 1.5. Divided by 0.5, is that 3? I think that's 3. Yay! Thank you, Marlon! Trois, un, deux, trois, dry, sun. Anyway, okay. I have, yeah, it's 3. Exactly, sun, right? Oh, I could, if I wanted to, I could show my kanji skills. I could show my kanji skills. I'm gonna write 3 in kanji. You know what? I did it. That's 3 in kanji. Okay. Kanji time! Okay, anyway. Okay. So, now we need to decide whether we reject or fail to reject the null. Well, we're going to reject the null, but just to draw out the distribution. Or should I say kanji jikan? Kanji also has something to do with wind, I think. Kaze. I don't know the kanji for wind. I don't know the kanji for wind. Now I need to know. This is why my students keep trying to diagnose me with things. Kaze, kanji. Yeah, okay, that's what I thought. It's... The kanji for wind is... Oh gosh, everything went everywhere. Oh, what have I done? A bug in a thing. Yeah, it's... I hope nobody's watching this who's familiar with stroke order, or they would judge me. That's my really sad wind kanji. Okay, right, okay. So, distribution looks like this. Our cutoff is plus or minus 1.96. There's 0. And then RZ value. There's also kanji for cold, which is also kaze. It's the normal wind kanji, and then the weird silent one. Oh, yeah. Yeah, like cold is in the common cold. Yeah. I was looking at that the other day. Yeah, that was totally wrong on my, you're good. Kanji's weird. And it could be like, maybe you're thinking of a different kanji that has to do with the concept of wind that does look like that. I was thinking, when you said that, I was thinking of kawa, like river. Looks kind of like a 3 on its side, but not really. Anyway, okay. And RZ was here. So that is definitely beyond the cutoff. I only know 15 hiragana characters. I mean, that's fair. There's a lot. There's like, what, 40... Is it 42 or 46? I don't remember off the top of my head. But there's a lot of hiragana characters and katakana characters. Anyway, we reject the null. Yeah, it's so easy to forget. I need to go back to practicing kanji. But, okay. But we're going to get through this. We reject the null. Because Mr. Kitty's getting restless. Isn't that right, Mr. Kitty? Oh, are you going to come up? You want to say hi to the people? Oh, you're a good kitty. Okay. I know, let's get through this, Mr. Kitty, so you can have lap time and snuggles. All right. So now we've got to interpret your results in plain language. Whichever language. Yes, he's Mr. Kitty. He's right here. He's full of rage because it's almost his dinner time, which means I might have to take a very, 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 very quick break in a moment. Imagine rejecting the null so close to Valentine's Day. Well, the alternative is failing to reject the null, which could be interpreting as ghosting the null, which I don't know how I feel about that. Yeah. Or just plainly. You're right. We could even interpret the results in a graph, which would just be like a pictograph. Plainly. Perfect. So, in this case, learning that a friend recommended a show made people significantly more likely to report they would watch the show than if they were given no information on the show. That, as a reminder, that's what we were talking about. Does getting a recommendation make you more likely to watch the show? Circling all the way back to where we were, which was a ways ago. Okay. Oh, okay. All right, so now let's talk about something called effect size. Actually, I'm gonna feed my cat really fast. So I'm gonna be right back, and I'm gonna do a drawing of my little man. I promise, I'm usually much better at art than this, but he's got a very fluffy mane. This is the stupidest cat I've drawn in a long time. Don't worry about it. This is how I used to draw cats in, like, 3rd grade. Okay, all right, I'm gonna be right back. I'm gonna feed my cat, and then I will return to you. And then we will talk about effect size. Okay. Okay, Mr. Kitty. There we go. I feel like starving a cat would be considered unethical. Exactly. You could also not feed your cat. And that could be, I would never not feed my little man. My little man deserves the entire world and everything in it. The ethics board wouldn't stop me because I wouldn't do it. My little man deserves the entire world. He deserves everything in the world and more because he's such a good little guy. He's such a good little guy. Okay. Need to get rid of all this. He deserves much better artistic depictions of him. He deserves the world. Okay. So, effect size. We've only really established that, like, getting a recommendation from your friend makes you more likely to say you're going to watch the show. So it's like a yes or a no. It's like binary, yes, you're more likely, or no, you're not more likely. We haven't determined, oops, sorry. We haven't determined how much. Test statistics like a z-test or a t-test, which we'll be talking about on Wednesday and all that stuff, they only tell you like, yes or no, is there a difference here? It doesn't tell you how big the difference is. It's kind of like, it's like a smoke alarm going off. It tells you, hey, there's something going on, but it doesn't tell you if that's like, maybe there's too much steam for the shower, or maybe there's a freaking like house fire or something. It doesn't tell you how big the thing is, it just tells you that something has happened. That's where the effect size comes in. So, like, describe the effect of, like, description of rating, personality on ratings of attractiveness. Describe the effect of getting recommended a show on likelihood to watch. Describe the effect of whatever. If it's a smoke alarm going off, does that mean I can use it for radiation experiments? That is not in my field. I have zero recommendations in that regard. I do not trust myself. I know nothing about that. I claim no responsibility. If something bad happens, it's not my fault. More antimatter? What are y'all doing over there? This is a classroom. We do not make antimatter in the classroom. Do that somewhere else. We are not properly equipped to deal with this. Oh, hello, Mr. Kitty. You're back already? Good job. Last steam was using the radiation source inside soak detectors and pesticides to make Oh my... Your last stream was... What? You're David. Oh my god, that's what was going on. Oh my god. Oh my god. I need to rewatch the VOD. I did not realize what was happening there. Oh my goodness. Y'all are getting up to some kinds of things. I fear. Okay. I'm going back to statistics because that's a nice, comforting, familiar thing for me. So yeah, effect size. We're talking about effect size. The effect size is Phi's favorite effect size that we're going to be talking about today. Cohen's d. Xenotime, I am concerned about you. Good luck. It's okay. The radioactive Boy Scout incident. I need to, like, get a notebook so I can write down all the things that I want to Google after this stream. This is so bad. Oh my gosh. Oh. Anyway, Cohen's d. Here's the formula for Cohen's d. It is the sample mean minus the population mean over the standard deviation. And this might look kind of familiar if you're familiar with other formulas that we're dealing with. It looks a lot like the z-score. It is doing basically the same thing as the z-score. The z-score for a single score was the single score minus the population mean over the standard deviation. It's just saying how far is the sample mean away from the population mean in units of standard deviation. The z-test for a sample mean is technically doing it in units of standard error. This is doing it in units of standard deviation. The bigger the Cohen's d value, the bigger the effect. The smaller is the Cohen's d value, the smaller the effect. And I think we're going to talk about that a bit more later when we get to t-tests. But for now, let's talk about power. Oh, I ruined my own joke. Not that power. We're talking about statistical power. I don't think she knows what statistical power is, but I could be wrong. I could be wrong. Okay. Statistical power is your ability to detect a difference between two groups and reject the null. So essentially, just think of it, your ability to reject the null, assuming that there really is something happening. Your ability to say these two conditions are different if they actually are different. Secret stats expert right there. You never know. So basically, if my independent variable has some kind of effect, will I be able to find that kind of effect? That is statistical power. The likelihood that if there is a real difference, your study will find it is your statistical power. There are a bunch of different things that affect statistical power. The first being the effect size. The bigger an effect you have, the easier it is to find. It's easier to find a real difference if it's a big difference. It's much easier to say that Oh man, I had a good example for this, but now all I can think of is my horrible cat example that I used to use because my cat is yelling and running around in the background. I love him. Um, okay, I'm gonna use an example that's kind of like a bit out there, but it's much easier to notice a big difference than a small difference. Like, it's much easier to notice if I moved every piece, if I moved every piece of furniture in your room, like to the opposite side of the room, that would be much easier to notice. That's a much bigger difference than if I moved every piece of furniture in your room a centimeter to the left, right? Like, it's easier to find big differences than small differences, so the bigger an effect you have, the bigger an effect you're looking at, the easier it is to find, the more statistical power you have. Hello, Mr. Kitty. He agrees. Another thing that affects power is your sample size. The more participants you have, the more statistical power you have. That's why with that example, when we only had one person who got $10 million, we didn't find a difference. But when we upped our sample size to 25, we did find a difference. The bigger your sample is, the more power you have, the easier it is to find differences. You can think of this as like, the more times you check for things. What am I doing? Mr. Kitty. Let's say you have some sort of food sensitivity, like milk, like lactose makes you sick. You're lactose intolerant. It's much easier to notice that if you drink an entire milkshake as opposed to if you have a teeny tiny sip of a milkshake, right? The more information you have, the easier it is to see something. You're getting a bigger chunk of the population too. We can also look at this mathematically. To find a significant difference, we want our z-value to be really big, so it can be past that threshold for significant. As your sample size increases, your standard error decreases. Your sample size is the denominator of your standard error. So the more people you have in your study, the smaller your standard error is. The smaller your standard error is, the smaller the denominator of your z-value is, the bigger your z-value we get. So it becomes easier to reject the null the more people you got. This is actually a bit like nuclear stuff, just to make a fun connection. I wish I could make that connection too, but I don't know nearly enough about nuclear stuff. Or drink multiple milkshakes at different times. Absolutely, that would also work. It's a lot easier to separate lighter isotopes than heavier isotopes because differences are much bigger. Yeah, it's a similar deal, I'd say. It's a similar deal. The bigger the difference it is, the easier it is to deal with. So yeah, in that way, it is very similar, I would say. That's a neat connection. I like that. And yeah, drinking multiple milkshakes at different times would also increase your sample size and make it easier to figure out lactose intolerance. Yeah, absolutely. That's more of a repeated measures design, I would say. But yeah. So bigger effect size, more power. Bigger sample size, more power. Power is also influenced by the variability of the population, the amount of variance you have. Some things there's very little variance. The number of arms on a human being, there is some variance in there. There are some people who have less than 2 arms and some people who might have more than 2 arms, but there's not a lot of variability. You probably have between like 0 and 2 arms on, like, most human beings probably have between 0 and 2 arms. That's not very variable, but there are other things that are incredibly variable, like, say, the length of your hair. That's a very variable thing. There's some people who don't have any hair at all. There's some people who have hair that is way many feet in length, right? There's a lot of variability there. The more variability there is in the population, the bigger your standard error, because you're probably not capturing the full spectrum in your sample if you've got a lot of variability in the population. You're probably not getting people with, say, no hair at all, or people with, like, hair that is, like, 6 feet, that's longer than they are tall in your sample if there's a lot of variability. If there's not a lot of variability, your sample's probably more representative of the population. Mathematically, the variance, or the standard deviation, which is a measure of variability, goes on top of the formula calculating your standard error, which means the bigger your variability is, the bigger your standard error is. The standard error goes on the bottom of the Z formula, so the bigger your variability is, the bigger your standard error is, the smaller your Z value is going to be. It makes it harder to reject the null. So as your variability increases, your power decreases. Power is also influenced by your alpha level. So alpha level standard in psychology is 0.05. As your alpha level decreases, as you go from 0.05 to 0.01 to 0.001, you get less power. It becomes harder to reject the null because you're essentially raising your standards. Null is so hot though, why do they get rejected? You know what? That's because that's how you get publications, and this is why many researchers... That's a lie. Many researchers are not single. I lied to you. But that's true. The null never gets accepted either, which is kind of sad. I think we said this earlier, yeah, but like you either reject the null or you fail to reject the null, and fail to reject the null can be interpreted as ghosting the null, I would say. You don't reject it, but you're not accepting it either. It's kind of sad. Somewhere out there a Bayesian is screaming, we have the power. We have the power to accept the null, or something like that. Somewhere out there a Bayesian is screaming, we're not like other guys. Oh my gosh, if somebody says ghosting the null in a paper, that will be my crowning achievement. Like, if that gets in a peer-reviewed paper, I will celebrate. There's a whole area of psychology that I see at conferences every year that studies the impact of ghosting in relationships, and that is like the perfect thing to do. Ellen and Bayesian are already on our route to your location. That's okay. If the Bayesians come here and attack me, I'll tell them that their priors are incorrect or something. I don't know. I don't know. Anyway, yeah, as your alpha level goes down, your power goes down, because lower your alpha level is actually raising your standards. It's making it harder to reject the null. The harder it is to reject the null, the less power you have. Their prior of your location was wrong. Perfect! All their conclusions are invalid. They have no idea where I am. They ended up on the moon. All right. So I'm going to do a little quick learning check. If you want to participate, you can. But this is a question that we went over way earlier in the lecture, so some of you may not have been here for this, but which test is more powerful? So we talked about which one was more conservative. Which test makes it harder to reject the null, a one-tailed test or a two-tailed test? Which one is more powerful? Which one makes it easier to reject the null? One-tailed or two-tailed? Oh, I should set up a poll. I'll call the poll power in all caps. One-tailed, and then two-tailed. So which one has more statistical power? Which one makes it easier to reject the null? It's been so long. Oh. Uh-huh. Uh-huh. Got 2 votes. It's perfectly tied. Does anyone want to be the tiebreaker? I just got here and I've been making cocktails. Can I take this test tomorrow? Yeah, that's fine. My V Theorem Academy, I believe, does offer makeup exams, and the lectures are recorded. All right, we got 3 votes in. I think I'll end it there. One-tailed is correct. So we talked about earlier, the two-tailed test is more conservative. It makes it harder to reject the null. Which means it's easier to reject the null with a one-tailed test. The one-tailed test is more powerful because it's easier to reject the null. Is that a good thing? It also means it's more prone to false positives. There are ways to make your tests more powerful without increasing your chance of false positives. Making it one-tailed is not one of them, unfortunately. So pros and cons of one-tailed tests. They're more powerful, but more likely to... Yeah, well, I record lectures anyway. And Phi, Z, and I, we record lectures in that our live streams automatically get VODs. Psy records lectures, but she posts them later, so they're not automatically posted. And I'm not sure about NEP. At least this stats class records lectures, by which I mean the VOD will be available. All right. Can anyone name me? Oh, I didn't realize Psy didn't have VODs on. She might sometimes, but I know that like she's been going through her backlog of VODs and like clipping them and then talking about uploading them and things like that. So she might have some VODs, but I don't think she has VODs for all of her streams, at least not public. Anyway, can anyone tell me something that affects the results of a significance test? She has a VOD channel on YouTube that she edits. Oh, that makes sense. Yeah, and Twitch does have a very different culture. So, very few people watch VODs on Twitch. Ah, I see. Yeah, I don't use Twitch all that much, so I'm not super familiar with it. The significance? I mean, yeah, I guess the significant, that's pretty broad, though. Can anyone give me something a bit more specific? Like, you're not wrong. The Playmaker's Evil Plans is absolutely not wrong. That is correct, but that's one of those sneaky answers that's like, you answered the question in a way I didn't predict. The alpha level, exactly, yes, the alpha level affects the outcome of the significance test. A higher alpha level makes it easier to reject the null. A lower alpha level makes it harder to reject the null. So there's one. Anyone got another one for me? Sample size, yes. Good job, hair dye. Hair day. You'd think I'd be able to pronounce day if I can pronounce. Anyway. But yes, sample size, absolutely. The bigger your sample size, the easier it is to reject the null. The smaller your sample size, the harder it is to reject the null. Absolutely. That is another thing that affects the outcomes. That's 2. I'm aiming for 5 total. Anyone got another one? I got the alpha, I can't talk anymore. The alpha, the sample size. What other things affected power? Alpha and sample size were 2 of them, but there was some other stuff as well. I'm putting a lot of pressure on chat already. I guess I usually do 5 things with an entire lecture hall, and this is less than an entire lecture hall. Maybe I'm not being fair. Yeah, the standard deviation and mean of the data itself. Yeah, so the variability is absolutely one of them, which falls, yeah, and the difference between the 2 measurements. Exactly. So the variability within the sample and within the population, both of those affect it. And the difference between the 2 measurements, the mean difference. Yes. Both of those things affect it. Yeah, so the things that I have listed here are sample size, power, which a lot of these things fall under power, variability, alpha, and effect size. But yeah, those things as well. Those also count. Good job. Okay, you survived. I have a little question thing here, so if like you have any questions from the lecture overall or anything like that, we can do that. And then I have some memes that I want to show you that are relevant to this. If we don't have questions, that's fine too. I can go make myself a hot chocolate or something. I want a hot chocolate. You have a question? Yes, Xenotime. How does this work with different distributions? Ah, yes. So this is a type of frequentist statistics, which assumes that you have a normal distribution. Once you start working with things like skewed distributions, it doesn't work that well. The problem here is that this is highly reliant on using the mean of a distribution as sort of like the typical score in a distribution. So we're summarizing the population as the population mean. We're summarizing the sample as the sample mean. But the problem with the mean in a skewed distribution is that it is heavily affected by outliers. It no longer, if you've got any like outliers or like you have a skewed distribution, it gets heavily affected by those outliers, and it no longer becomes typical of like a typical score in the sample. So what if it's T instead of normal or something? Oh, we'll talk about t-tests starting on Wednesday. T's all right. Like we have ways of dealing with T, but like if in general, if like say the population distribution is not normal, technically the central limit theorem kind of addresses that problem, but it's still something you definitely need to be careful about, because the mean is not a good measure in non-normal distributions, and z-scores and a lot of these statistics rely heavily on using the mean, so it becomes unreliable. Yeah, the central limit suggestion, I would like to call it that. We have ways of dealing with T, spoken like a true American. I'll drink tea. I like tea. I like tea. Maybe I should make some tea after this just for that. Oh, that's hilarious, though. You are so right. All right. Let's do our. I can feel my voice kind of giving out on me. I don't know if you can hear, but it's getting a little scratchy. So let's get to those memes. All right. So I'm gonna explain some jokes to you. Is it true Americans don't have kettles? I have a kettle. I have an electric kettle. I do. I didn't for a long time, but now I do. Now I do. I got it as a celebration for getting my PhD. And that's what I'm gonna use to make my hot chocolate, actually. Yeah, see, we have kettles. But well, I don't know, actually. I think actually a lot of Americans do have kettles these days. You have three. I guess I technically have two, because the person who had my office before me left her kettle behind, and now it's mine too. So technically I have one kettle at home and one in the office. But I don't use the office one. I have one, but Brits would laugh at it. That's fair. I don't know if Brits would laugh at mine. I think they would just laugh at mine, like, based on principle. Two don't work. Oh, that's fair. Electric kettle is incredible. It has definitely changed my quality of life. That said, it is louder than what I did before, which was just boiling a pot of water on the stove. Anyway, if your alpha level's 1, there's a 100% chance you're rejecting the null. Like, of course that means there's an incredibly high chance you're making a type 1 error, but like, if your alpha level's 1, you're rejecting the null no matter what. It doesn't matter, and whether you're wrong or right. We have hard water, so we get so much limescale. That's unfortunate. Here on the dorms, so having it in my room is so much nicer. Oh, I bet. Yeah, when I was in college, I did not have a kettle in my dorm, so we would have to go all the way to the dining hall if we wanted tea. I guess I could have made it in the microwave, but like even I feel like that feels like sacrilege, you know? Even as an American, I have some standards. All right. So the typical alpha that we use in statistics and a lot of other fields is 0.05. So that explains this meme. An alpha of 0.05 means we can expect a type 1 error about 5% of the time. About 1 in 20 hypothesis tests that we reject the null on will probably be a type 1 error. So that's why, what is the statistician? A person whose lifetime ambition is to be wrong 5% of the time. Also, the microwave in my dorm room has a big sign saying, "Science microwave, no food." Oh, is that the one that you used for your stream? Oh my gosh. Oh, yeah, I bet that must be the stream one then. Scary. All right, type 1 error. Yeah, for both streams you've done. Oh, you've done another. I missed it. Am I subscribed to you? If I'm not, I need to subscribe to you. I love you, microwave. Scary. All right, so this one. Finally, a p-value of less than 0.05. This would be finally, yeah, we want significant p-values because they help us publish. It's very hard to publish results where you fail to reject the null. So I've seen videos for melting iron. That sounds like something that Xenotime is doing. Aren't they great? I've just found them. I didn't make them. I just found them around. Not all effects are meaningful. So in this first few lectures and later on when I talk about correlations, we talked about spurious correlations. These are like meaningless correlations. So just because you reject the null doesn't mean it's meaningful. Sometimes there might be associations that just are completely useless or meaningless. And then, let's see. Low power increases your chance of a type 2 error, so my data looking at a significant effect but is stopped by low statistical power. Here's another one. Low power increases, so another type 2 error one. My experiment with poor statistical power. Significant finding, completely missing it. And it's very difficult to deal with both type 1 and type 2 error. Many attempts to reduce your chance of a false positive increases your chance of a false negative, and a lot of the ways that you can decrease your chance of a false negative increases your chance of a false positive. It's not a perfect relationship. You can sometimes lower the chances of one without raising the chances of another, but it's tricky. Low power also stops you from approaching people. Me too! Me too! Took 3 pages of notes. You took notes? Oh my gosh, that's awesome. Taking more samples always helps both though, right? Yeah, bigger sample sizes help both most of the time. There are cases where having, like, if you get a big sample size, but it's from a really shitty population, like, or well, not a shitty population. If you get really shitty sampling, like a really biased sample, let's say I get a huge sample, but it's a whole bunch of bots taking my survey, which is a problem that some psychologists have been having for the past 5 years or so on online surveying platforms. Your sample size isn't going to save you if your data is low quality. It's still going to have a lot of problems with type 1 and type 2 errors, but generally speaking, increasing your sample size will lower both. I have all your notes. That is so awesome. I'm so happy. Thank you. That's the last meme I have though for now. We've been going for nearly 2.5 hours. This was not the intent. I think that's counting the time before stream though, so maybe not the full 2.5. If the sample is from a uniform population, then that's true. Yeah, well, like, everything's complicated. You know, nothing's perfect. More people in your sample is usually a good thing, but like, yeah, it's not a perfect solution, you know? Yeah. I mean, well, depending on where you get your sample, with psychology, like, your sample's always people, and it's pretty much impossible to get a perfectly random sample of humanity. Yeah, there's always exceptions to everything. It's like, you get far enough in any discipline, the answer to any question is going to be, it depends, or, you know. You are so good at keeping track of numbers, Astrologopos. I'm so jealous. Thank you. Yeah, I guess I've just revealed to you that I sat here with my stream all set up for 15 minutes before I actually started, because this is my first time streaming a lecture on my new PC, so I wanted to make sure everything was set up. So I started to get it set up probably way earlier than I needed to, and then I just sat here staring at my screen for 15 minutes until it hit the time. Oh. But yeah, that's all I got for today. Thank you all so much for coming. Thank you for dropping in. I had a lot of fun. I hope that you enjoyed it too, and I hopefully, I know I've learned things today, like the 5 standard deviations in particle physics. Well, for me it started at 30, so the maths is easy. That's true. Yeah. Yeah, thank you. I will be live again. Like, of course, no one has any obligation to come, but I'll be talking about one sample t-test on Wednesday, starting at the same time. So that's 7:30 p.m. Eastern time on Wednesday. I will be talking about t-tests. Oh, all right, I'm going to get a glass of water, and I'm going to go give my cat cuddles and scritches. Thank you all. Oh yeah, I'm glad. I do my best to make things as digestible as possible. That does mean I'm often simplifying stuff a lot, but like, I'm doing my best. Oh, I'm glad. Thank you, everyone. Thank you so much for coming. Have a great night or have a great day, and get plenty of sleep. I'm looking at some of you who I know are in time zones where it's probably the middle of the night. Yeah, take care, everyone. Bye-bye.